Hi everyone! Here's a video which you may find interesting if you are a software tester who wants to know more about state-driven testing, or perhaps a mathematician with a graph theory background. I would like to show in this video an example of a non-Eulerian digraph, which we will transform into an Eulerian digraph. This has an impact on the test design when we try to cover the state diagram. Why am I talking about graphs and state diagrams at the same time in this video? For a tester, a state diagram consists of certain states which describe the behavior of a system and the possible transitions of a system. For a mathematician, a graph consists of nodes and edges, which are also called vertices. In the case where the edges in a graph have a direction, we may speak of directed arcs, and the graph is called a digraph. So what does it mean when we say a graph is Eulerian or non-Eulerian? A simple explanation is, when you try to cover a graph by drawing with a pencil, you may start at a node, cover all edges once and only once, and come back to the start without lifting the pencil. In this case, the graph is called Eulerian. In the case where you have to lift the pencil to cover the graph completely, the graph is called non-Eulerian. In case you are not familiar with the terms Eulerian and non-Eulerian and wish to get some insight, I strongly recommend watching Colin Haggerty's YouTube video about the Chinese postman problem, which covers this topic very well. Before we take a look at an example which I would like to show you, please let me introduce one more concept, which is the adjacency matrix. This matrix is a representation of a graph. The numbers within an adjacency matrix describe which nodes are connected by edges or directed arcs. So the adjacency matrix captures the information about who are the next neighbors of each node in the graph. In case where we see the graph from the perspective of a software tester, the adjacency matrix describes the previous and next states in the state diagram. We will see this shortly in this video. Let's have a look at the example. On the right-hand side of this slide, we see the digraph or state diagram. It consists of three states S1, S2, and S3. How are the different states connected? Looking at the matrix on the left-hand side of the illustration, S1 is connected to S2. Row S1, column S2 contains a 1. You will also see that S1 has only one state that can happen afterwards, which is S2. So the total count of outgoing states in row S1 is 1. Similarly, the count of incoming states for S1 is catered for by the column. S1 has one incoming connection, S3. Row S3, column S1. In the case of S2, it is connected to S3, and therefore we also have a 1 in the second row of the matrix. Row S2, column S3. S3 is connected to two states, S1 and S2. That's why the number 1 appears twice in the third row of the matrix, and therefore the total is 2 in this case. Let's come back to the graph on the right-hand side and have a look at each individual node of the digraph. We start first with the node S1. You can see that there is one incoming edge and one outgoing edge, so both numbers are equal. Let's check the next node, S2. Here we have a different situation. S2 has two incoming edges, but only one outgoing edge. So these numbers are not equal. We have a similar situation for S3. Here we have one incoming edge and two outgoing edges. So here is the point. In order to make a digraph Eulerian, we have to make sure that for each node the number of incoming edges and the number of outgoing edges is actually the same. In case the digraph is non-Eulerian, we have to add edges. So the task is to draw an additional arc between S2 and S3. How can we see this in the adjacency matrix? Let's try to find the matrix element which needs to be changed. The sum of the column S2 is 2, which are the two incoming edges of S2. The sum of the row S2 is 1, which is the outgoing edge of S2. In order to change the sum of the row S2, it looks like we have to change the value in that row, which is 1. Let's check node or state S3. The sum of the column S3 is 1, which is the incoming edge of S3. The sum of the row S3 is 2, which are the two outgoing edges of S3. So in order to change the sum of the column S3, again it looks like we have to change the value in that column, the number where the two green rectangles are overlapping. When we do this and increase the number in the second row and in the third column by 1, we get one more edge, the additional edge between S2 and S3, and we see that all sums are now equal, which means that our digraph has become Eulerian. What does this mean for the tester who is trying to cover the state diagram with 3 states, S1, S2, and S3 with test cases? It looks like now, as we have an Eulerian graph, we can draw along all edges without lifting the pencil, or create one single test case which covers all states and transitions. Let's see this in detail on our state diagram. The way this single test case is designed is that we start at state S1, and the first test step or transition is from S1 to S2. The second transition goes from S2 to S3. We now go back from S3 to S2. Then we use the edge we had added and return from S2 to S3. The last step of our test case is to do the transition from S3 to S1. We now see that the state diagram is completely covered, and we were able to cover it in one single test case because we added an additional edge, and by that we made the underlying graph Eulerian. I hope you enjoyed this video and found it helpful.